Good day everyone. Today we shall be studying Stoichiometry 1, under which we shall consider obtaining moles of various substances. By the way, this is Gifted Brain aka Saizu, first in Africa, sixth in the world. Stoichiometry is derived from two Greek words, stoichion and metry. Stoichion, which means elementary particles, and metry, which means measurement. So in literal terms, you can say stoichiometry is the measurement of elementary particles. And when we say elementary particle, we are simply referring to protons, electrons, neutron, atom, molecules, ion, formula units, etc. Actually, elementary particles are elementary particles of matter. In chemistry, stoichiometry is actually the study of quantitative or measurable relationship that exists in chemical formulas and chemical relationship. It's one of the most important topics in chemistry, and the reason is because most calculations in chemistry are considered under stoichiometry. And now the approach we want to take to this study is the mole approach. And what is a mole? A mole is the amount of a substance that contains the Avogadro's number of particles. If I say a mole of electrons, I simply means that when you count those electrons given, it is 6.02 times 10 raised to power 23, which is the Avogadro's number of particles actually. If I say a mole of pencil, for instance, if you're counting those pencils, you should have 6.02 times 10 raised to power 23 pencil there available. So, and then the mole is essential. Why are we taking this approach? Because the mole is essential. It relates several quantities in chemistry. For instance, there's a relationship for mass and its molar mass expressed in mole. And then mole also relates volume and concentration. It relates volume, pressure, temperature, etc. So that is why the mole approach is one good way of studying stoichiometry. Some relationship expressed in mole. These relationships are very, very important because on and on we keep referring to them. For substance of known mass, if you are given the mass of a substance, and it's easy to get the mole by using mass over molar mass, the mass in gram, take note, and then the molar mass in gram per mole. For elementary particles, remember I said they refer to proton, electron, neutron, atom, molecule, ion, formula units, etc. And so if I'm referring to elementary particles, then you should be using the number of particles given to you over 6.02 times 10 raised to 23, which is the Avogadro's number. And for a solution, how do you get mole? It is concentration times volume. And for a gas at standard temperature and pressure, how can you get mole? It is volume over 22.4, which is the molar gas constant. For an ideal gas, it is PV over RT. Your P can be in atmosphere. Be sure that your volume should be in dm cube and temperature in Kelvin, and your R is molar gas constant, which is 0.0821 atmosphere dm cube per mole per Kelvin. But if your pressure is in Newton per meter square, then be sure that your volume should be in meter cube and your molar gas constant changes to 8.314 joules per mole per Kelvin. The temperature remains Kelvin. Let's take some example under this study. Example 1. Evaluate the mole present in 10.24 gram of H2SO4. Given that hydrogen is 1, sulfur is 32, and oxygen is 16. The first thing to ponder on is how do I get mole in this question? And for the fact that we are given 10.24 gram of something, takes my mind back to the relationship we have earlier. The best relationship that suits this is the mass relationship, because since we are given mass, we can use mass over molar mass to get the mole. The molar mass of H2SO4, molar mass of H2SO4 is given as, the H, we have two hydrogen here, so it is 2 times the molar mass of hydrogen is just 1, and then plus sulfur is just 1 here, and then the molar mass of sulfur is 32 given to us, and then finally plus oxygen, we have 4 oxygen here, and the molar mass of oxygen is 16. So this will just give us 2 plus 32 plus 4 times 64, 16 will give us 64, so which is 98 gram per mole. So this is the molar mass. So the mole here will be just mass over molar mass. over molar mass. And obviously, the mass given to us is 10.24, and the molar mass given to us, we've obtained, is 98. So eventually our answer is, 0.1 mole. That's the answer. Example 2. Calculate the mole in 3.01 times 10 raised to 3 atoms of sodium. Another thing that comes to mind is, what relationship can I use to get mole here? Obviously, if you're telling me atoms, then I should be using elementary particles. Atom is one of the elementary particles. And so hence, my mole here should be the number of particles given to me, number of particles over the Avogadro's constant, which is 6.02 times 10 raised to 23. Yes, the number of particles given to us is 3.01 times 10 raised to 22. And then all over 6.02 times 10 raised to 23. Upon evaluation, we have 0.05 mole. This is the unit, mol dot. Number 3, example 3. Evaluate the mole present in 200 cm cube of 0.1 mole per dm cube of NaCl solution. For the fact that this is a solution, going back to our relationship, one of the ways to solve this is using concentration times volume. So my mole is simply concentration times volume. Another thing here is that the volume is given in cm cube. I should convert. To convert, just say 200 over 1000, and that will give us 0.2. So it's 0.2 dm cube now. Hence, I will just simply say concentration is given as 0.1 mole per dm cube times the volume, which is 0.2. So upon evaluation, we have 0.02 mole. Example 4. Find the mole in 8 dm cube. 8 dm cube. So this is 8 dm cube, not 8 per dm cube. 8 dm cube of hydrogen gas at STP. So if I'm to evaluate this 8 dm cube of hydrogen gas at STP, so to evaluate this actually is to say that mole, since it's a gas at STP, just now mole is given as the volume over 22.4, which is molar gas constant, 22.4. So the volume given to us is 8 all over the molar gas constant is 22.4. So my answer is equal to, the answer here is equal to 0.357 mole. Yeah. Example 5. Evaluate the mole present in 200 cm cube of an ideal gas, exerting a pressure of 0.935 atm. And for this question, we simply use PV over RT. So my mole is PV over RT. Yeah. The pressure here, P for pressure, and the pressure is given as 0.935. But the volume is in cm cube, so I have to convert to dm cube, so which is 200 over 1000. I'm doing my conversion now, and that will give me 0.2. And again, I'm also given that my temperature is not in Kelvin, it's in degrees C, so I will have to say 40, which is what is given, plus 273. So this will give me 313. So eventually, I will have that pressure, which is 0.935 multiplied by my volume, which is 0.2, all over molar gas constant is given as 0.0821, then times temperature, which is 313. So at the end of the day, our answer is 0.007 mole. So thank you.